Okay, so today we will be talking about something which is also a part of physics, but before that, let's get to the what are complex numbers. Okay, complex number, not numbers, number, which is the one I equal square root of -1. This single discovery changed everything. Whatever we found hard and couldn't solve by the discovery of I or complex number complex number, everything changed. Everything changed. Everything everything changed. Now easily wherever we had problem we could use complex number to solve it. So first of all, what are complex numbers? Complex number could be defined as imaginary numbers, numbers which don't exist. For example, we know that -1, or we cannot take we cannot not take square root of -1 or minus any number, any number. So what we did is that we assigned square root -1 like we made it a constant. Okay, and this constant can be said in a way that in terms of algebra it will be known as z equal a plus minus b, where a is a real number minus b, since b multiplying with minus, so it will give us imaginary number. So b is a imaginary number, and the answer is that this gives us a real number. Okay, this gives us a real number. And the opposite of z, which is conjugate of z, is z star equal a minus ib. Same again in both. What is common is that a is a real number and b is a complex number. Okay, so how could we think of the complex number is that, let's suppose if we have a complex space. Okay, in this complex space, the y-axis or the y-axis is defined as a, y-axis is defined as the b or minus b would be fine, and the complex number is the middle. This one is the complex number. Okay, this is the complex number in terms of the space. Complex number. Okay, so then what we say is that if, let's suppose we have the same space, but in this space we have the complex number, and we want to find the a values of a and b. So, and this is theta. So Oh no, not it. We don't have to find where b. We have to find this number z, and what we have is this value theta. So to find z, now what we do is that we do something known as, we know that an angle between the horizontal or the x-axis and the resultant, this we call it result in terms of physics, I would call resultant, is cos theta. Okay, and angle which is not in between, the opposite, is sine theta. Okay, so what we get is this z equals cos theta plus sine theta, and this actually is our complete. We have to add I so that we get a real number. This is the correct way. It's the same as saying, this is being replaced as z equal a plus ib, where a is cos and b is sine theta. So, and one more thing, this equals e I theta. Remember that. Okay. This is a complex thing that we have solved, so we don't do that. So then this, so then complex numbers are both important part of physics, important part of physics and math. Okay, important in physics and math. Okay, and if I relate it to so then complex numbers are imaginary numbers, numbers which are not real, they don't exist, and but still they are used in, if I talk about QM, quantum mechanics. In quantum mechanics, the use of complex number is in the main equation of quantum mechanics, which is Schrodinger equation. Okay, so how, let me show you. I h bar d over dt psi of x psi equal h d h what is this, psi? Yeah, so here psi is actually a complex number, because we know that complex numbers are imaginary numbers. So what we do is, this is how it should be like. It, because of its property that it carries information than a real number alone could. Okay, it carries more. The one benefit is that it carries more information. Okay, and one more thing over here was that we know that z, if we have over here, where is it, this one over here, we know that a plus b square root equals to the this thing absolute of z. So then this would convert to a square plus b square equals to absolute z square, where they are real number. It gives a real number. Okay. Mathematical consistency with the Schrodinger equation. The Schrodinger equation, which governs the which governs which governs the evolution of quantum states, is a, yeah, wait, isn't in quantum states it's also used? Because what we know is that psi, what we know is that psi is what? Psi is what? Psi is a psi is a probability density for a particle to be found at a certain point. So alone, when we don't take its square, it's a complex number, but the moment we take its square, it turns into real information. Okay. uh, the moment the moment the moment it's taken square root of, it turns into a real number. So the probability, or what we call this is, what we call is, wait, let me just do one thing, and I would like that it would be simple. I just want to settle everything on one page. Okay, so actually this probability square is nothing but this and this. Okay, and yeah, over here same thing, this one will equal conjugate of z and z, multiple of them, where so this is the conjugate over here, this is a conjugate of psi, and it represents the probability of finding a particle in a certain region, given space or certain region, how you would take it as. The use of a complex number function ensures that probability densities remain real and positive, because we cannot have probability as negative, then it would not make sense, which is crucial for the physical interpretation. Always what we say is that whenever we talk about the QM, whenever we talk about QM, we want to make everything a real or physical interpretation. Okay, so these are, we have to take the probability density, we have to make a square so that it can be taken as a physical interpretation. Superposition and interference, how complex numbers allow wave function to naturally describe interference patterns. Okay, so in interference patterns observed experiments like double slit experiment, the complex phase in psi leads to constructive. So we know that the Schrodinger equation, of course, the main equation, Schrodinger equation, is what helps us talk about these complex numbers. So when we talk about an example of quantum, not quantum, complex number, here, if let's suppose I have an example here, z, the example could be z equal 3 plus 4. Here, when we talk about, so what do you say? This 3 is taking place of A, and this 4 is taking place of B. So 3 is a real number and 4 is an imaginary number, and I is the imaginary unit, where we know the magnitude. Okay, now you know this over here is nothing but a magnitude. But where is it? This one. This is nothing but a magnitude. So we could also find the magnitude So we could also find the magnitude or the unit of these by doing what? We could just do square root of 3 square plus 4 square is what? 9 and 16 plus, so that equals to 25 plus 25, so we get 5. So that's our magnitude, which is z. In quantum mechanics, again, such complex numbers are used because, again, amplitude and phase are one important parts of quantum mechanics. And just to say, like, tell complex numbers are, even though they're imaginary part of math, imaginary numbers. Okay, let me give you one more example of complex numbers. Let's suppose if we have a quadratic equation. Okay, we have a quadratic equation. A square, sorry, what was it? Ax square plus bx plus c equals 0. We know that in quadratic equation, let's suppose if we have a quadratic equation and we make a graph of it like this. So what are the x-axis? Is that the point where the graph intersects, right? The x-axis. So if we solve the equation, if we get the answer in terms of complex number, we know that the values given show, if it's a I complex number, we know that the x-axis don't exist at that point, and so we can say that at that point it's at a complex number state. Okay, because this is x-axis, this is y-axis, so it would be at a complex number state. So it would be same as, what I think is that it would be like this over here. If it goes like this, okay, so it is like this, b a I. Okay, so it will be like this. It would be like this. And same goes for other graphs as well. If it's a quadratic, the point, if it doesn't touch, this is how it would look like if it touches the x-axis. Okay, here it is touching, so it would be 1. So, and even for a cubic, there's one x, there's the second x. Okay, yeah. So there's no x-intercept, not x-intercept. Okay, so no. That's it. Thank